This is Steve Tockey, principal consultant at Construx Software. Welcome to today's Construx Lunch and Learn. The topic today is Software Engineering 101. In the background, I've got Jesse and Eric that are going to assist with the Q&A. So as we're going through, if you do have a question, feel free to use the Q&A tool. They will accumulate them up. They'll try and answer them as best they can if they can on the fly. But they'll queue up the questions and we'll talk about all the questions at the end. So let's dive in here. There's some obligatory legal stuff. The goal is to talk about understanding one key difference between true software engineering and what is computer science, what's known as computer science in mainstream practices. I mean, people tend to use the word software engineering as interchangeable with the word computer science, and it's really not. And what people do in terms of mainstream practices does not really qualify in terms of what really software engineering is. Mary Shaw, Carnegie Mellon University, quote, "Given our track record, there are fundamental problems with the use of the term software engineer." I wholeheartedly agree with that. And so really the point is let's look at what engineering really means as defined by the people who are already recognized as being engineers. And I should add here, it's very important to understand that at least in some jurisdictions, use of the word engineer, it's actually a legally reserved word. It's like calling yourself a lawyer when you're not. It's like calling yourself a medical doctor when you're not. It's like calling yourself a pilot when you're not. That in some jurisdictions, the state of Texas, for example, the state of New York, all of Canada, use of the word engineer is a legally reserved word, and only certain people get to call themselves engineers, having satisfied some set of criteria, much like a medical doctor, or as I said, a lawyer or an airline pilot. You must satisfy some set of criteria before you can use that legally as a job title, because it sets certain expectations against the people that you're working with. So that's where we're going. Let's dive in. We're going to have a little bit of introductory material. I'm going to define what engineering means to the already recognized engineers. That's the point. If you're a chemical engineer, if you're a civil engineer, if you're an industrial engineer, they have already defined what the term engineering means. And so if we use their definition of what engineering really means, and oh, by the way, that is the legal definition, that if we take that definition and apply it in software, well, let's see what happens. And so as a consequence of that, one of the issues is how decisions are made. And we'll go into a fair amount of detail on that. Okay. So the first question I want to ask is, why are companies in business in the first place? And I hope you realize that companies have their mission statements. Yeah, and that's fine, okay? And some companies say, oh, we're in business because it's fun. And some people say, oh, we're in business because it's educational. And some people say, oh, we're in business to have a positive impact on society. And I would propose that those are reasonable secondary reasons. They are secondary reasons. They are not the primary reason. This may come across as crass and blunt, but the reality is, those businesses are in business to make profit for the owners. If the company does not make a profit for the owners, then clearly it doesn't stay in business for very long. Non-profitable businesses do not stay in business for very long at all. Which then leads to the obvious follow-on question, I would hope: where does the money come from? If a business is in business to make money, then what do they do to make money? And I think the obvious answer to that question is they make money by selling products and services. What are the products that your organization sells? What are the services? Those are the source of the income that your company runs off of. Wonderful. But then it also becomes a very interesting question to ask: where is the money going to? We know where the money is coming from. Where is the money going to? And so let's look at that. Across the top here, gross revenue, that is all the money that is coming in based on your sales of products and services. That's everything. That's all of your income. Now, the biggest chunk that comes out of that is the cost of goods sold. How much does it cost you for materials and labors to be able to create the goods and the services that you're selling? And understand that that's a fair chunk of the gross revenue. Now, the next chunk out of the gross revenue is operating expenses, just keeping the company running, keeping the fires burning, if you will. All of the selling expenses involved, all of the general administrative costs involved, taxes that are not income taxes. And once you've taken out cost of goods sold and operating expenses, what you have is your operating income. Now, most organizations, most companies actually operate to some extent on borrowed money. They're not necessarily self-profitable enough that under certain conditions they need to work with borrowed money, and that's fine. But if you're running your company on some degree of borrowed money, then understand that part of what you have to pay out is interest on those loans, and that's this interest on loans element right here. Depreciation, it's a long and involved topic, but just understand that if a company buys $1 million machine to be doing work, that they don't get to take away the $1 million cost of the machine in the year that they bought it. They actually have to spread that $1 million cost over several years. That's what depreciation is all about. Now, once you've taken away the investment related expenses, you now have net income before taxes. This is what you're actually paying taxes on. Income taxes is actually a misleading term. You're not paying income taxes on gross revenue. You're paying income taxes on net income taxes, net income before taxes, which then leads to you having to pay the income taxes, federal, national level income taxes, state level income taxes, provincial level in Canada, etc., local income taxes, etc. Now, after you've paid all your income taxes, that gives you net income after taxes. And if you're a company with stockholders, you're not required, but you may pay dividends to those stockholders, which is again coming out of the original gross revenue. So that money goes directly to the stockholders as a reward for investing in the company as dividends, and what's left over is retained earnings. Okay, so this is kind of abstract, but let's get really specific here. And I kind of randomly chose Peoplesoft, and I kind of randomly chose 2003, but this is a representation, this is a representative example of the kind of things that we're looking at for a software organization. So 2003 Peoplesoft, gross revenue $2.267 million, or approximately $2.25 billion of gross revenue. 38.3% of that original $2.27 billion got spent in cost of goods sold. That's what it cost them to provide the goods and services that they did provide in that year. Operating expenses were $1.28 billion. That was 56.6%, leaving an operating income of $117 million, which is 5.2% of the overall gross revenue that they brought in. Now, a very interesting aspect of Peoplesoft Corporation is, for whatever interesting reason, instead of borrowing money, they were in a financial position that they were lending money to other organizations. And so the minus $22 million that you see here is actually interest paid to Peoplesoft on money that they loaned to other organizations. And so rather than it being a positive number because they had investment related expenses, they were actually getting investment related income. It's kind of an interesting situation. So their net income before taxes was $139 million, or 6.1% of the original $2.27 billion that they brought in. Now, They paid $53 million in income taxes, 2.3%. Let me jump on this very quickly. This is not big corporation avoiding taxes. This is 2.3% of gross revenue. Very important, 2.3% of gross revenue, but you're not income taxed on gross revenue. Remember that you're income taxed on net income before taxes. And so if you take the 53 million and you divide it by the 139 million that was the taxable income, you'll find out that their actual tax rate was 38.1%. So they were, I would argue, at least in the dimension of being of taxation, they were being a good corporate citizen by paying nearly 39% income taxes. Okay, that left them with a net income after taxes of 85 million, which was 3.8% of their gross revenue, at least for that year and maybe for many other years. Peoplesoft philosophy was not to pay dividend. Your value in the company doesn't come directly from the dividend. It comes from the increase in the stock price, and some companies operate that way. That's fine. Okay. But the real point that I'm trying to get across here is simply that, you started off with $2.27 billion that once you took away all the money that you had to spend just to stay in business, you're left with a total of $85 billion, 3.8%, meaning that 3.8 cents on every dollar of gross revenue was the money they had left around to do the interesting things that they wanted to do. Key point, companies don't have a lot of spare money laying around to do things with. There's a lot of other expenses that are further in line ahead of, oh, we want to do something interesting. There's just not a lot of money to be playing around with. Now, one key indicator of a company's health is the profit margin, and that is where you take net income after taxes and you divide that by gross revenue. And remember, in the Peoplesoft case, that was the 3.8%. So 3.8 cents out of every dollar represented the actual profit of the company. Now, profit margin is actually very industry specific. Some industries tend to have high profit margins. Some industries tend to have very low profit margins. In fact, the more competitive a market is, the more competitive an industry is, typically the lower profit margin. Grocery stores, for example, are often running on fractions of a percent of profit margin. But as the joke goes, they make it back up on volume. Okay, so again, the key point here is there's just not a lot of money floating around for people to be frivolous with. That there's some pretty tight belts going on in most companies. So now, how expensive is software? And I need to introduce the term, if you're not familiar with it, full-time equivalent, or FTE, which is generally between $150,000 and $300,000 a year. Now, it varies geographically, it varies, etc. But this is not how much the company pays in salary to a software professional. No. Take what your salary is and then add on top of that benefits, and then add on top of that the facilities, and add on top of that paying the electricity bill, and add on that the heating bill and all of the overhead. And when you add up the cost of all the salaries and all the benefits and all of that other overhead for the software people and divide it by the number of software people that you have, that gives you the actual cost of hiring somebody for a year, which is well over the salary cost. So the point here is that software is really expensive. If your FTE in your organization is $250,000 a year, which it could easily be, that every 4-person years is $1 million in expense. Now, the top 5 challenges in software development lunch and learn that I did earlier goes into this in much more detail. And so I don't want to spend a lot of time here. I want to refer to you to that lunch and learn. But the harsh realities are that software projects really don't perform very well. Many projects fail to deliver any usable software, which is clearly a loss. Projects are chronically late, they're chronically over budget, they're chronically under scope. And again, for more detail, go see the top 5 challenges in software development lunch and learn topic. It will definitely open your eyes if you haven't seen that. Now, again, if you go over there, you'll see that I blame the top 5 reasons as things like vague, ambiguous, incomplete requirements. Well, yeah, that's on this list. You'll see that I blame things like inadequate project management, and there it is on the list. I blame things like uncontrolled design and code complexity, and here it is. And I blame things like overdependence on testing and not having adequate maintenance documentation. It's the self-documenting code myth. Now, underneath all of them, if I take one more step back, here's my point. If I take one more step back between why do we have vague, ambiguous, incomplete requirements? Why do we have uncontrolled design and code complexity? I'm arguing that it comes down to the cost of bad decisions. Somebody is making a decision which is not a good decision under the circumstances. And so keep in mind, that's the key. The ultimate root cause is going to have to be something having to do with somebody made a decision that was not the right decision. And so now I want to go into the whole topic of what is engineering. And again, the key here is to say, okay, if we're going to define software engineering, shouldn't the definition of software engineering be in some way consistent with the definition of civil engineering and the definition of chemical engineering and the definition of mechanical engineering and the definition of aeronautical engineering? And so shouldn't we base our definition of software engineering on the already, if you will, legally defined definition of what engineering is per the people that are already recognized formally as being engineers? So there's an organization, it's called the Accreditation Board of Engineering and Technology, ABET for short. And so they are one of the organizations that have to do with dealing with engineering as it's legally defined. And they define engineering as the profession in which a knowledge of the mathematical and natural sciences gained by study, experience, and practice is applied with judgment to develop ways to utilize economically the materials and forces of nature for the benefit of mankind. So that's their definition, and that's essentially the legal definition of engineering. Engineering is this profession in which, fine. So what I've done is taken that half a paragraph definition and distilled it down to the single equation. It would be fair to summarize engineering, I propose, as, on the one hand, using scientific theory and using practice. And I'm using the theory and the practice to come up with potential solutions to a real world problem. I'm coming up with potential solutions, and then I'm judging the potential solutions organized by theory against economics. And so there's a whole field called engineering economy, which is all about engineering decision making, as you're going to see in a moment. And I should point out that if you go to school and you get a civil engineering degree, you are required, this is not an elective, you're required to take a class in this engineering economy. And we will be looking in more detail at engineering economy today as we go in, as being one of the key differences between true engineering and what we do in software. And so, for example, let me just toss up that this is an example of a university textbook that somebody would have to use in their engineering economy class. And there are a number of them, and just in case you happen to be interested, this is the very engineering economy textbook that my dad used when he got his electrical engineering degree at University of Nebraska in the 1950s. And he thankfully saved all of his textbooks, and when I was in high school I went through some of his college textbooks, read this book, and reading this book as a high school student is really what got me set down on this path of, well, if you're going to be an engineer, let's really understand it. Okay, so adding a little bit more detail here, the first book I showed you was written by Paul DeGarmo and some others. They kind of summarize engineering as finding the balance between what is technically feasible and what is economically acceptable. The second quote comes from a guy named Arthur Wellington, who is recognized as, if you will, the father of engineering economy. He was in the 1880s, and so the whole discipline of engineering economy was kind of kicked off by Arthur Wellington. He certainly wrote the first textbook on the topic. And he's got this interesting quote here: "It would be well if engineering were less generally thought of or even defined as the art of constructing. In a certain sense, it is rather the art of not constructing, or to define it rudely but not inaptly, it is the art of doing that well with $1, which any bungler can do with $2." And you may have heard variations on that saying over the years. An engineer can do with $1 what any idiot can do with $2. Well, it all traces back to Arthur Wellington and his first engineering economy book that was published in 1887. So if that's what engineering is, then software engineering should be the profession in which a knowledge of the mathematical and computing sciences gained by study, experience, and practice is applied with judgment to develop ways to utilize economically computing systems for the benefit of mankind. And so in equation form, if we want to be consistent with the definition of engineering, if we want to be consistent with the recognized definition of engineering, that software engineering should involve computer science and practice as the underlying, how do we generate possible solutions to some practical problem, together with engineering economy. And I'm just showing you books that summarize, if you will, the computer science and practice aspect of things and the engineering economy aspect of things. Leon Levy wrote an interesting book, but in that book, it's a wonderful quote: "Software economics has often been misconceived as the means of estimating the cost of software of programming projects. It's not. Economics is primarily the science of choice, and that is the key thing. Economics is not the science of money. Economics is the science of choice. And software economics should provide methods and models for analyzing the choices that software projects must make. Yes, engineering economy is all a set of methods and models and tools that are all about making economically appropriate choices, making the right choice, making the right decision. So if I go back to software being a good way to spend a lot of money and not get a lot of value out of it, it all comes down to making the wrong decisions. And how do I drive to the right decisions? And that's where the economics comes in. So let me go look at fundamentals of engineering decisions. What is the engineering process? And so this diagram here is starting to show you, at least at a high level, what the engineering process is. Yeah, I want to start by understanding what is the real problem. Maybe the problem that they're telling me that they have is not really the problem that they have. So a little bit of using techniques like 5 whys, et cetera, et cetera. I want to make sure I really understand the problem that needs to be solved and not the problem they immediately tell me needs to be solved. Then I'm going to be using the theory and the practice to be coming up with reasonable, technically feasible solutions. These are things that we could do. In parallel, if you will, I can define the how am I going to decide which of the things that I could do is the thing that I'm going to do. And there can easily be multiple selection criteria in which money is not the only criteria, but usually money is in the set, and usually it's the largest driver. It doesn't always have to be. But again, then knowing what my selection criteria are and knowing what are reasonable, technically feasible solutions, then I'm going to evaluate those against these selection criteria. The one that scores the best is the preferred proposal. That's what we're going to do. And oh, by the way, it's not just blindly jump on that. We want to monitor it over time. If we made the wrong decision in some way, we have to be able to circle back and change it to something that's more appropriate. And so A consultant friend of mine, Myler Page Jones, characterizes it this way: it's the science and the practice that allows us to set up the candidates, and it's the engineering economy that knocks them down. And the last one standing is the one we go with because it's the one that's most economically viable. Okay, and so part of this involves this whole notion of a proposal. And so I'm just going to skim through at a high level the topic of engineering economy, engineering process, engineering decision making. And part of it involves this notion of a proposal. It's a single thing that we could do. It's a binary. We could do it, we could not do it. It involves some choice, yes or no. Do the alpha project, enhance beta, reorganize the gamma code base into microservices, move to the cloud. They're all different levels of decisions, and whatever level of decision you're making, that involves, if it's a binary decision, do A, do not A, then it classifies as a proposal. Fine. Cash flow is all about the financial view of one of these proposals. Cash flow instance is a specific amount of money at a given point in time that's flowing into or out of the organization as a direct result of that proposal. If we decided to do the beta project, then in the third month of the beta project, we would have to pay the development staff payroll some amount of money because I have some number of developers. And that development staff payroll in the third month of the beta project, should we decide to do it, would be an example of a cash flow instance. And the cash flow stream is the set of all the cash flow instances over time that would be caused by this proposal, both in terms of income and in terms of expense, and it would be the financial view of this beta project as an example. Now, because these cash flows and cash flow streams are very key elements of doing engineering decision making, there are a lot of tools around them, and one of the tools is called a cash flow diagram, which fairly simply just allows me to visualize what does the cash flow stream look like for some proposal. And I'll show you where this came from and how I came up with it, but this is just, let's introduce the topic of cash flow diagram. There's an initial investment which has to do with money that you had to spend just to get started. It's like your admission fee. If you want to do this, you often have to pay some amount of money just to get started, just to get out of the starting gate. Then, over time, running from left to right, arrows above the zero line represent net income. Arrows below the line represent net expense. And so what we're saying is that whatever this project is, it starts off with a huge investment. And the second year, when I combine all the income with the expenses, it's still net negative. There's still a loss in that year, but it's certainly a lot less. And then the next year, I'm saying profit, et cetera, et cetera, et cetera. And so this would be a fairly typical cash flow stream for a brand new project where we had to pay to develop it. We get some ramping up income over the initial years of the product, and then a gradual tailing off of revenue over time as we continue. Okay. There are categories of cash flow, and the reason I'm bringing this up is just to give you the understanding of how does one go about developing a cash flow stream. And so I talked about initial investment, that's your price of admission. There are operating and maintenance costs that you have to pay after you started that basically continue through retirement. There's the sales income, and there is something called cost avoidance. Sometimes the thing that you're doing does generate direct revenue, and that's fine. Everybody understands that. But sometimes the thing that you're doing does not itself generate direct revenue. What it does is it reduces the cost. And since profit is revenue minus expense, I can increase profit by increasing revenue, or by decreasing expense. And so cost avoidance has to do with the I am attacking the decreasing the expense side of the equation. I am not attacking the generate more revenue side of the equation. And salvage value has to do with, after all is said and done, is there recoverable value in assets? So really quickly, if you want to become a one-person taxi cab company, then fine, understand that you've got to go buy the taxi cab, and that's your initial investment. And then over the years that you're operating your personal taxi company, you've got to be paying gas, you've got to be paying for oil, you've got to be paying for window wiper fluid, you've got to be paying insurance. All of those are the operating and maintenance costs of running the taxi service. Now, clearly, if you're in business with a taxi to make money, the fares that the people pay to have you drive them from here to there, there's your sales income. Now, at the end of I'm done driving a taxi, then presumably you should be able to sell the taxi to somebody else for some amount of money. That would be the salvage value that you have in the taxi cab. Okay, and so that's just kind of a really quick example of how I would apply this. Now, the cash flow diagram that I showed you a little bit earlier, this was for a proposal to develop a payroll package, a payroll processing package at some mythical company, let me call them Mountain Software. And so they happen to name all their projects after mountain ranges, and so this Alpine payroll package. Now, it's going to cost them $250,000 just to get out of the starting gate. Now, what they're estimating is 9 developers in the first 2 years as the investment in developing this brand new payroll package, and 3 maintainers in the remaining years to do the necessary maintenance on it. And that their full-time equivalent happens to be $225,000 per year per developer. Now, of course, income. Yes, this is a product. They're going to sell it. They're going to get sales to brand new customers. They're going to get upgrades to existing customers. They're going to have maintenance contracts for some portion of their customers. And maybe they're offering training classes, and customers are going to pay to come to the training classes. And there are the products and services that they're selling that generate their income. Now, what I have on the top here is by year estimated units. 9 developers in year 1 and 2 to do the initial software development, 3 developers in the remaining years to do the ongoing maintenance. How many units of sales are we estimating? How many units of upgrades are we estimating? How many units of maintenance contracts are we estimating? How many training classes are we estimating, etc.? Now, what I've got down here, since I have up here the unit estimates, here are the cost revenue per unit. Each developer is going to cost us $225,000 fully burdened. Each new sale, $600. Each upgrade, $100. Each maintenance contract, $145, etc., etc. So now it's a simple matter of taking the estimated units and multiplying them by the unit cost. And you see those units times the corresponding unit cost in each of the years added across each of the rows gives me this net cash flow. And so these are the cash flow instances net at the end of each one of these years of if we were going to do this project. Here is its financial view. And what you should notice is that all of these numbers here precisely match the numbers here. And so this is the cash flow diagram for this Let's Do the Alpine Payroll project. And so you get a sense of how I look at a project and I look at the different kinds of costs and incomes, and I use that to build up this cash flow picture that gives me the financial perspective of the project. Wonderful. Now, a very key element of economic decision making is this notion of interest, the time value of money. Yes, time is in fact money. Gary Larson of The Far Side has a fascinating comic where he shows Albert Einstein standing at the board, and it looks like he's deriving E equals mc squared, but in fact what he's deriving is time equals money. And it's a great joke of the punchline is that Einstein discovers that time is in fact money. It's a wonderful comic, can't show it. I've asked Gary for permission to use it. He says no, so there's copyright issues involved, but we can talk about the concept. So time is money. A given amount of money at one time does not have the same value as an identical amount of money at a different time. That money, amount of money, and value are actually two different concepts. And it's actually rather easy to illustrate. And so if I was to pick randomly from the set of attendees that are attending here, I'm not going to do this for real, I apologize, because it's a little bit expensive, but imagine that we had this lottery. One member who was in the listening audience, congratulations, you just won $100. And so imagine that I had the ability to reach through the internet and give you, on your desk in front of you, $100. Wonderful. Now I'm going to randomly select some other attendee, and I'm going to say, well, it's your lucky day as well. However, instead of getting the $100 today, you're getting the promise of $100 next month. So I have these two people, person A, $100 today, person B, $100 promised a month from now. Who's better off? And I think it becomes rather clear here that the person who gets the money today is in fact better off. Why? Because they have the money today. They can spend it. They can invest it. Whereas the other person doesn't have the money today. They have to wait for it. There's a promise. And you know, promises sometimes get broken. So they can't use the money until it shows up. And there's also a certain risk that the money won't actually show up as promised. And so now the question to be asking is, would the person who was promised, person B, $100 a month from now, be willing to take less than $100 to get the money today? You can get $100 a month from now, or you can get money today, but it will be less than $100. Would you be willing to take $99 today in exchange for $100 a month from now? Would you be willing to take 98? Would you be willing to take 97? At what point do they say no? And for example, if they said no at $94, they'll take 95 today in exchange for $100 a month from now, but they won't take 94 today in exchange for $100 tomorrow, or a month from now. Then we've established the time value. That money today is worth $5 less than that amount of money later, okay? And just the same with the person A, who I've said you get $100 today. Would you be willing to wait a month before I gave you the money? And the answer is no. If it's only $100, no, they're not going to be willing to. They want it now. But if I promised 101 at the end of the month, if I had promised 102 at the end of the month, if I promised 105 at the end of the month, and if I promised 106, at what point does their decision go from no to yes? And it's that difference between the $100 today and the what does it take in the future, or the promise in the future, what are you willing to accept less today? That is the expression of the time value of money, that some amount of money, $100, does not have the same value today as $100 has a month from now. Time is in fact money. And that time value is quantifiable, and that's what we know as the interest. Interest is literally rental. You are renting somebody's money. You're not renting the car, you're not renting the apartment, you're not renting the house, you are renting somebody else's money, and interest is the rental fee that you're paying to use some other person's money. Now, archaeological evidence dates back to 2000 BC. There's clay tablets wherein you see repayment schedules and agreements to pay interest. And so this is a very ancient concept. It's not something new by any stretch. And so the interest rate is, in fact, the rental fee that's expressed as a percent of the amount that's being borrowed. I agree to borrow from you this amount of money at a rental rate of, for example, 6.825%. Now, we're going to assume that it's an annual interest rate. Don't worry about that for right now. Now, the shocking thing here is I just want to point out that a recent poll of American high school seniors asked the question that if you went to the bank and you got a loan to buy a house or a car, is the amount of money that you pay back by paying loan payments the same, less, or more than the amount that you borrowed? And over half of high school students and high school seniors in America thought that if you borrowed $50,000 to buy a hot car, that you made all these payments, so as you're paying it back, that the amount of money that you paid back was the $50,000 you borrowed. They had no concept that the amount of money that you're paying back is actually more than the $50,000 you borrowed, because you have to rent the money for the time that you're using it to buy the car. And I thought that was a rather shocking survey result. The people really need to understand this much better than they do. Now, there are a bunch of mathematical formulas that if I have some amount of money at some point in time, and I want to look at an amount of money at a different time, and I want those amounts of money at different times to have the same value, how do I move the value through time? There are a set of interest formulas that allow us to do that. And they're just standard entities, elements in these formulas. P, what's it worth today? F, what's it worth in the future? I, what's the interest rate? N, how much time is between now and then? A is not a single value, A, annuity. It means it's a stream of equal recurring payments. And so it's not a single point, it's a series of equal payments over some amount of time. So just so that you understand, that's what we're working with here. Now, simple interest, really easy to understand. The amount of interest you pay is directly proportional to how much you borrowed, how long you borrowed it for, and the interest rate. And so the formula I equals P times N times I, that the F you pay back later is the P plus I, which basically boils down to P times 1 plus NI. If you borrow $15,000 for 5 years at 8% simple interest, expect to have to pay back $21,000. 15 for the amount that you borrowed and 6 for the interest. Fine. Okay. Now, the problem here is that simple interest favors the borrower. The borrower wins under the simple interest scenario. The lender is lending this money, but they're not getting interest on the part of the loan which is unpaid interest. So it works out rather simply this way. You borrow $15,000 for 5 years at 8% compounded interest. Then the $15,000 that you borrowed for the first year at 8%, you now owe $1.2 $1,000. So what you owe at the end of the first year is $16.2 thousand. Now here's the trick. Going into the second year, you don't base the interest on the $15,000 you borrowed. You base it off the $16.2 thousand that you now owe. And so when you take 8% of that at the end of the second year, you owe this. Now, if you start the third year with this, and you take 8% at the end of the third year, so you start the fourth year. Now, the important point here is understand that after 5 years, you owe $22,000, and notice how this compares back to the $21,000 simple interest. And so there's $1,000 of interest difference with compound interest than simple interest, and this all gets down to simply interest on interest. And so, of course, the modern golden rule, which is he who has the gold makes the rules, of course, the lender is going to want to do things in their favor, so the lender demands compound interest. So that's what we're going to be working with. There's a whole set of formulas that basically take some amount of money at some point in time and move it over to some other amount of money at some other point in time that has the same value. And that's the key. I want to preserve the value, but I want to move the amount of money from here to there. What does it do to the amount to preserve the value? Single payment compound amount, the simplest formula, again, compound interest. So the future value is equal to the present value times 1 plus the interest rate raised to the time power. So borrow $15,000 at 5 years at 8% compounded. The point here is, yes, I still got the $22,000 that I worked out manually, but I'm trying to introduce the idea that because these are very common issues in making engineering decisions, that there are shorthand notations, and this is how I would solve the problem. In a practical sense, there are formulas, there are calculators, there are interest tables. How did I get this factor 1.4693? Well, I looked it up in a table. That if I have money today and I want to move it to the future at 5 years with 8% interest, here's the factor, multiply this by this, and presto chango, there I am. This is the formula for computing loan payments. If you are borrowing some amount of money at some interest rate for some amount of time, this is the underlying formula. Here is the shorthand for how you would figure out what the loan payment is. Now, I need to caution you here that I am assuming right here annual interest rate. And if you have a house loan, you're not paying annual interest, you're paying monthly interest. And so what you have to do is take the annual interest rate and convert it into a monthly interest rate, which is a non-trivial but still doable thing. But you could, in fact, check the bank. If that was my amount borrowed, if that was my annual interest rate, turn that into a monthly interest rate. If that's how many months I have to pay on the loan, you can double check the bank and figure out that, yeah, the loan payment that you're making on that loan is in fact the right payment. There are other formulas, again, for taking money now in the future, moving backwards, and the annuities, et cetera, et cetera. So I'm not going to go into these in any detail because we don't have time, but I'm just showing you that they are out there. Now, comparing cash flow streams, the point here is, as an example, company sells a product for $20,000. Some customer says, hey, I don't have $20,000. I can't pay you that today. What I'll do is I'll pay you $2,500 at the end of each of the next 10 years. And so the cash flow stream for pay now looks like this, and the cash flow stream for the pay later looks like that. And so the question is it in this company's best interest to take this pay later option? Because kind of on the surface, it does look like the pay later option is a better option, $25,000 versus $20,000. But the important point to make here is that implicit in this analysis is ignoring the time value. This is taking an interest rate of 0, and the real interest rate is not likely to be 0. What happens if we use a more reasonable interest rate, say, for example, 9%? Then you see that $2,500 over 10 years at a 9% interest rate, when turned back into money today, has the value of $16,044 today. And so again, would you rather have $20,000 in your pocket today, or would you rather have the value of $16,000 in your pocket today? Because that's the real value of this cash flow stream. Now, if you want to get the same value of $20,000 today, but spread it out over equal payments for over 10 years at 9%, that customer will have to pay you $3,116, not $2,500, but $3,116. And said another way, that if you would accept $2,500 over 10 years in lieu of $20,000 today, that is essentially an interest rate of 4.27%. And so I'm just trying to get across the idea that the time value of money is real, And using interest rates of 0 is not really necessarily a wise idea, that in our business decisions, we need to account for the effect of interest. And so this introduces this concept of equivalence. 2 or more different cash flow instances or cash flow streams are equivalent. They have the same value only when they're the same amount of money at the same time. Okay, more specifically, comparing 2 different cash flows makes sense only when they are expressed in the same time frame. And that's what I was illustrating with the $20,000 now or $2,500 at each. They were not in the same time frame. If they had the same value at the same point in time, then they would be equivalent. And so it's the equivalence, or said more precisely, it's the lack of equivalence that is really the basis for making economic decisions. So if they are truly economically equivalent, it really doesn't matter which one you choose. But if they're not economically equivalent, then you take the one which is more favorable to you. So it's the lack of equivalence that I'm really after. And so as a consequence of that, there are these things called bases for comparisons, which I take an entire cash flow stream and I move it into some equivalent representation format. There are a number of them where we don't have time to go into them, obviously. I'm just going to focus in on present worth. And so here's the formula for present worth. Essentially what I'm doing is I'm taking my original net cash flow stream. So this is the Alpine Payroll project. And I'm looking up the factors that for each of the years would take that amount of money at that point in time and convert it back to the equivalent value of this amount of money today. That amount of money at that time, at that interest rate, then has the same value as this amount of money today. And so I'm just running through all of those cash flow instances, equivalencing them back to value of money today, and now they're all in value today terms, and I add them all up. And so the present worth of the Alpine payroll project is $874,000 today. So the financial value of doing that project is like that amount of money in my pocket today. And so now I'm ready to get into how you make really legitimate engineering decisions in for-profit organizations. And I have to introduce this concept of a minimum of attractive rate of return. And so look, in a nutshell, this is your opportunity cost. If I am confident that I can get a rate of return of X% by doing B, then if I'm going to do A instead of B, I have to judge A in light of what I could get in terms of B. And so if I could get 13% by doing B and I can do A, I need to judge A in terms of the 13% that I could get if I did B instead of A. And so it's this minimum acceptable rate of return that we're using as the interest rate in for-profit engineering decisions. And so there's more detail about it that we don't have time to go into, but just understand that there is this concept of a minimum acceptable rate of return. There are factors that influence this minimal acceptable rate of return, and these are the factors that the organization's management should be taking into account and judging and establishing that in our organization, engineering decisions over the next time period should use a minimum acceptable rate of return of X, whatever X happens to be. And so you might think back to that profit margin for the company. If your profit margin happened to be 12%, that meant that just continuing to do what you're normally doing should net you 12%. So you might want to think about using this 12% as the minimum acceptable rate of return as a going in. Okay. Now, so the for-profit engineering decision process involves arranging all of the different things that we could do in order of increasing initial investment. I just assume that the first one is the best one, but then I just sequentially go through and compare, is the next one better than the current one? So look, simply, this is a max function. I'm just looking for the maximum. Now, the reason that I'm sorting them in order of increasing initial investment, and the reason that I'm looking for strictly better than, is simply to say that if two things have the same value, but one has a lower initial investment, the one that has the lower initial investment is the better choice, because I get the same value out of a lower initial investment. So there's just a little bit of gory detail in there. But let me run through a really quick example of an actual for-profit engineering decision. I have 4 different things. Now understand, this quote, do nothing proposal doesn't mean really do nothing. It means do something else. Take the money that you could have used to do either of any of these things, and don't do this, just do something else. Invest it at your minimum acceptable rate of return elsewhere in the organization. And there are reasons why you would normally want to include a do nothing, or I should say do something else alternative. And it just means don't do any of the things that we're thinking about here. As I said, just do something else. Now, it costs you nothing to do something else. One of the proposals is to restructure the Sierra benefits package into microservices, and its initial investment is $190,000. We could develop the Alpine payroll package, and as I showed you when I developed that cash flow stream, that its initial investment was $250,000. Another alternative, or another possible thing to do, is to move the URL's HR package into the cloud. Yeah, we could do that. Initial investment, $285,000, whatever. So here are the 4 things we could do. Something else, refactor this guy into microservices, develop this thing from the ground up, and move that guy to the cloud. Those are the things that we could do. The organization, because of their profit margin, et cetera, has established a minimum acceptable rate of return of 12%, and they've said, I want to be looking at the next 7 years as the planning horizon. Fine. And so when I look at the present worth at 12% of the do nothing, or better said, do something else, the present worth of 0, it's 0. Okay, fine. Now, if I look at the Sierra project, which has $190,000 initial investment, because it's the next up on initial investment, and I run the present worth on its cash flow stream, understand that its present worth at 12% is minus $29,000. And this is the important point, that given some cash flow stream and even given some interest rate, that proposal is not actually guaranteed to be profitable. And here you have an example of something that's not profitable. And so you see, if I had to choose between doing something else and doing the Sierra benefits into microservices, that I'm better off doing something else, because this one loses me money. Now, if I look then at developing the Alpine payroll project, that I'm looking at present worth at 12%, and you saw how I calculated that earlier manually using each one of those present worth factors, and that was $874,000. Now, I hope it's rather obvious that $874,000 as a present worth is worth more than $0, and it's certainly worth more than minus $29,000. And so this guy is currently the best alternative. Here is the winning candidate right now. And so what we have to do simply is now look at let's take the URL's HR package and push that guy out to the cloud, and let's run through, and its present worth is $157,000. But now you see $157,000, yeah, that's a lot of money, but that's less than the 874. So this guy is still the best. And so once we've run through all of them, the last person standing is this guy. This one has the highest present worth of all of them. So economically, even though the other things are things that we could theoretically do, practically, economically, this is the best course of action because it has the best rate of return. Now, again, if that guy came out negative, if that guy came out negative, and if that guy came out negative, then 0 would be better than a string of negatives, which means don't invest in anything that you got here. Go invest the money somewhere else. Okay. Now, really quickly, I just want to point out that the book Return on Software, if you look at the outline here, this is essentially the same outline in terms of course content. with what's in this book and what's in that book and what's essentially in my dad's engineering economy book. This is just standard curriculum. But the message here is threefold. Message number one, the things that are underlined here are topics that we touched on in today's Lunch and Learn. There's much more detail under each of those topics. Also, understand that there are other topics that we didn't even talk about. So this is a much deeper subject than we've been going through here. I'm just trying to introduce. So message one, we've only touched on a little bit. There's a lot more. Message two. Message three is that these methods and these models are actually quite useful for your own personal finance decisions as well. You want to buy a house, there are several options for house loan. How do you decide which one's the best? You use these methods and models. Do you refi your house or not? Well, that's what these methods and models are good at. You want to buy a car? Should you lease a car? How do you save for paying for college tuition? How do you plan for your retirement? I should point out that this is intended to be a college textbook. It's got questions, homework assignments embedded in it. And one of the homework assignments in one of the chapters is literally plan your retirement. And so I kind of want to toss out the idea here that you might not need to pay a financial planner a whole lot of money to plan your retirement for you. When all the tools are at your fingertips, you could plan your own retirement and save all that money. So let me wrap up here and say that we had some introduction. You know, there's not a lot of money left around. Software projects are a good way of spending a lot of money and not necessarily getting a lot of value out of it. I defined engineering, and then I said, well, if software were defined engineering in the same way that engineers defined engineering, then this is what it would have to be. We went through some fundamentals. We took a high-level skim, the top of the waves, look at how this all works, and now we're summarizing. So key points in all of this: companies are in business to make a profit for their owners. Yeah, fun, educational, do good for the community. Those are all secondary reasons. But look, if you're not making a profit for your owners, that you're not going to stay in business very long. Most organizations don't have a lot of extra money just lying around. We need to be careful with the money we have. Software projects in particular tend to end up wasting a lot of money without getting a lot of return on that investment. That the summary is that engineering could be summarized as use of theory and practice on the one hand to create potential solutions, and use of engineering economy on the other hand to select which of those potentially viable solutions is the most economically practical. Economics is not the science of money. Economics is the science of choice. Real engineering means balancing technical feasibility with economic acceptability. Engineering economy is the set of methods and models that help you find that balance. And these same methods and models are quite useful in your own personal finances. And so it really comes down to, in the end, if you're not basing your software technical decisions, at least in part, on engineering economy, then you're not, by definition, according to the legal definition of software of engineering, you're not really doing software engineering. And so that was the key message here. Go ahead and use software engineer as a job title, but understand that to the real engineers, to the people that are legally recognized as being engineers, they behave differently. And so maybe we ought to think about behaving differently to align our definition of the job title with their definition of the job title. So hopefully you now have an understanding of one key difference between true software engineering and computer science. They are not equivalent terms. And what we do today. And so given our track record, there are fundamental problems with use of the term software engineer. This doesn't mean that we couldn't resolve those problems. That's my point. This is how we would go about resolving these problems. But certainly today, I agree with Mary Shaw. You want to call it engineering? It's not, sorry. If you want to track down the references, they are all here. That's fine. And so now let me throw it over to Jesse and Eric, and let's start taking questions from the vast listening audience.
Okay. The one that I would like to put forward is that this is a pretty intimidating topic. I suppose that if a person works in an organization with a finance group that is very adept at all of these concepts and applications, then you could find some willing accomplices to make this happen. But let's suppose that our listener is working in an area, a company that doesn't have a well-developed finance kind of thing. They're spinning up their company, they're moving on. And is there a crawl, walk, run to this, or is it just a ledge I have to climb?
Oh, I would agree that crawl, walk, run. Okay. So what I did today, because as I said, this is a much deeper topic. What I did today is crawl. And so if you can understand the crawl that we did today, then understand that you could look at the other time value of money equations next month, and you could look at other basis of comparison the month after that, and you could look at planning horizons in economic life. I said that this mountain software company chose the planning horizon to be 7 years. How did they do that? Well, it wasn't number out of the air. There was a process for how they came to the 7 years. And so you could sequence these topics out over easily a year or two if you really needed to. You don't need to deal with inflation and deflation today. You don't need to deal with income taxes today. You just have to start paying more attention to the financial side of things. And so let me just, it was last summer, I was with a particular company, and I'm not going to mention who they were, but I was working with a particular project, and I saw in their design that they were using REST. And to my technical evaluation, yes, you could use REST in this application, but this is not the place where you should have used REST. It was overly complex. It was too much overhead. There are a number of reasons. They should have just used a standard RPC microservices-y kind of approach. They should not have used REST. And I asked them, well, why did you use REST? And their answer was literally, well, because RPC is too old hat. RPC is not what people are doing today. It's not the, as I would call it, the fad of the year. And that's not how you behave in a profit-making company, especially if you're a stockholder in a profit-making company. Okay, RPC may have been old hat, but it was the most cost-effective solution to the problem that you had. And going off into REST, because they had never done REST before, and because it added a whole bunch of complexity, it was not the right engineering decision. Too many decisions on projects today are made because it looks good on a resume, not because it's the financially wise thing to do. And that's a problem that needs to be solved.
So what I hear you saying is that even a basic application of what you've talked about today is going to do things like focus attention on the hinge factors that people are using to justify their decisions. And that's got to be good to put sunshine into a dark place like that.
Yeah, you don't have to be the expert to know everything, but at least just start paying attention to the money. Because you want to go the REST route, fine. Let's talk about going the REST route. Let's talk about not going the REST route. Now, what does going the REST route do in terms of schedule, in terms of cost, in terms of complexity? And we can put dollar signs on all of these things. And until you can show me that going the REST route is more financially viable than going some other route, then I'm questioning why we should go the REST route. Because if it looks great on your resume, I don't care about what looks great on your resume. I'm an owner of this company because I'm a stockholder in this company, and I care about what looks good for the company as a whole, not what looks good for you on your resume. So does that make sense?
Yeah, and I think your element of time value of money plays in here, because we need to look at REST and the assumptions under the decision about, is it the right thing now, but we'll have to rewrite it completely in 5 years, but to do RPC versus REST, or should we spend the money now to make REST and hopefully keep it for 10 years? And being able to calculate that is useful.
Yeah, and that's where we are now engineering the software. We are looking at a cost-effective solution to the business problem. Yes, that's what engineering is all about.
So one other question has come in from Greg, also known as Anonymous.
Okay.
how do you keep time to complete it from being the dominant term in software engineering decision-making at the team level day to day? And I assume this also relates to something I thought of as you were speaking today around Don Reinertson's exhortations around if you quantify nothing else, quantify the cost of delay.
Well, ask the question again. I'm not sure I got my mind around it.
How do you keep, and in quotes, time to complete it, unquote, from being the dominant term in software engineering decision-making? There's something I think hidden here, and Greg, we're on a time delay, so you're 30 seconds back, but there's something here, I think, in terms of sunk cost fallacy and looking at only how much time is left to complete it and deciding based on that. There's maybe some nuance to this, but does that make more sense?
Yeah, and I'm not sure I'm going to be able to get at that nuance here. And so, anonymous Greg, whoever you are, my email address, steve@construx.com. We can continue this offline. But the best answer I can give you right now is, again, these are proposals. We can look at this, schedule, deadline, whatever, and what are the consequences of it? What does the cash flow stream look like if we do that? Now, what does the cash flow stream look like if we do something else? And if I compare the cash flow stream of doing that to doing something else, and I find that doing something else is the better thing to do, then here's my justification for doing something else.
You're right on here because Greg has elaborated how to express the future value of different choices. And any brief, obviously that's a huge topic too, but any brief advice for how to express the future value of different choices aside the sunk cost fallacy and cost to complete.
Yeah, so let me just put it this way, maybe, is that in the chapter on replacement and retirement decisions, that's where sunk cost fallacy shines. And that's a whole other discussion for a whole other time. But I think I would summarize it down to answer Greg's immediate question is, look, there are things that you could do. We could do A, we could do B, we could do C, we could do D. Now, if we do A, it looks like this. If we do B, it looks like that. If we do C, it looks like that. And if we do D, it looks like that. Now, financially, economically, of all the things that we could do, that guy is the most lucrative. So
yeah, I like that. It sounds as though in Greg's wording that cost is the major driver of decision making rather than cash flow, and people aren't comparing the various cash flow options of the approaches. They're only looking at what does it cost.
What does it cost me today rather than what is it costing me over time and what is the revenue over time? Yeah, that's a fairly common thing. We cost accountants. Cost accounting is the death of software engineering. That's a whole other discussion for a whole nother time.
Well, and that leads to one last question we'll have time for here from Ken. How does this change for an organization where the project comes from a signed contract and the decisions are just on implementation?
So how does this come from
fixed bid contract has been signed and your only real flexibility is apparently here decisions are just on implementation in Ken's question.
Okay, and so if this is the Ken I'm thinking it is, hi Ken, good to see you. Part of this has to do with maybe we should have been careful about how we set up the contract in the first place. There were different ways of establishing the contract and, we could do it this way and the cash flow would look like, and we could set up the contract that way and the cash flow would look like. And so I'm saying that quite possibly that the issues that he have here might precede establishing the contract in the first place. But the other side of this is, given that the contract sets up a financial view like this, that all of our decisions have to be based inside of the financial constraints of the contract as we agreed on it. So rather than going, if you will, forward from here's what we could do, here's the financial view, you work it backwards. Here's the financial view that's legislated by the contract, and here are the things that we could do given the constraints of the financial view the contract already. So you just work backwards, I would suggest.
Yeah, and obviously this changes if you have a fixed bid contract where the objective of the provider becomes cost minimization to maximize profit versus time and materials where the objectives are flipped. and that
Right, right. Yeah, contracting terms can drive some very interesting variations in behavior. Yep, yep.
All right, we have exhausted the list of questions, and I think we're about out of time. So,
Okay, great. Thank you, Eric. Thank you, Jesse. Thank you, everybody, for attending, and hope to see you at future Lunch and Learn events. And as I said, if you want to contact me directly, just pop me an email, and I'll answer questions offline. So thanks again, everybody, and we'll see you later. Bye.